This is the continuation of our series on advanced mathematics for data scientists. At the end of this video, I want you to have a grasp of this theorem. Homology and cohomology have found their applications in AI also. We have a kind of neural network called simplicial neural network, which are a generalization of the graph neural network. The building block of homology and cohomology are simplexes. A point is a zero simplex. A line is a one simplex. And a triangle is a two simplex. We can have higher simplexes, like the tetrahedron is a three simplex. We have a map which we call boundary map. The boundary of a line is the 2 points that it has, and the boundary is shown like in this slide. Boundary of the two simplex is its three edge, so we can write the boundary map of the two simplex like that. We have a lemma that says the boundary of the boundary is 0, so this is always 0. If we take the boundary of something twice, it will result to 0. Here we calculate the boundary of the two simplex. If you do the calculation, you will get 0. We can define a chain complex by a map which goes to lower complexes. We can define a group H subscript n, which we call the homology group, and is defined by the kernel of the delta n map divided by the image of the delta n plus 1 map. We can now define a cohomology also. In cohomology, basically we have the same simplex structure, but the arrows are reversed. This is a summary of what we have discussed so far. So we can define homology groups and cohomology groups by the kernel and the image of the maps, and it is the language of cycles and boundaries. So this theorem that we talked about is called Doran theorem. You see that this theorem is about cohomology now. The right part is defined using the simplicial complexes, and the left part is about manifold. So let's see some review of the manifold. In the manifold video, we defined the manifold to look like Rn. And also we defined a tangent space at the point, and we defined the bases of the tangent space and the bases of the cotangent space. Also we defined something called the differential forms. So this theorem is basically about the bridging the simplicial complexes and differential forms. A differential form is something that its fate is to be integrated over. So you can see example of the 0 form, 1 form, or 2 form. We have a differential form called the exterior derivative. You can see that you have something like the chain complexes, but it is defined on the manifold. And we have a rule that looks like the fundamental lemma that we discussed. So this is the exterior derivative of the forms become important. A closed form is a form that its exterior derivative is 0, and an exact form is a form that is the exterior derivative of another form. You can define a cohomology group on this manifold by this quotient of closed form and exact forms. As a side note, you can see the Stokes theorem on a manifold, which also relates the differential with the boundary map that we discussed so far. So finally we have our theorem. It is telling us that these two groups are isomorphic. Whether we use calculus to define it or we will use simplicial complexes, it is a bridge between these theories, and it is very nice. And finally we have the quote by Poincaré, which says, mathematics is the art of giving the same name to different things.